Hello, this is Meteorology 113, Lecture 8, Ground Level Ozone. This is the second lecture of course Module 3, Outdoor Air Pollution, Ozone and PM 2.5. The outline of this lecture is as follows. We will first give an overview. We will summarize the main adverse health effects of ozone. We will then present a historical perspective for appreciating ozone's importance in air pollution. We will then review how ozone is distributed vertically throughout the atmosphere, distinguishing between ozone in the stratosphere, ozone in the troposphere away from pollution sources, and ground level ozone in urban areas, which is the focus of this lecture. We will then cover the formation processes of ground level ozone. These involve a series of chemical reactions involving sunlight, termed photochemical reactions, which form ozone from precursor nitrogen oxide or NOx emissions and volatile organic compound or VOC emissions. NOx and VOCs were among pollutants covered in earlier lectures. We then present some efforts to control NOx and VOC emissions aimed at reducing concentrations in the future. Ground level ozone overview. This slide summarizes the main health effects from inhalation of high concentrations of ozone. The graphics are taken from the EPA websites shown on the bottom. Ozone, if inhaled in high enough concentrations, can inflame the passages of the airways, leading to trapping of air in alveoli, the tiny sacs terminating the airways deep in the lungs that bring air in contact with the bloodstream. The inflammation of the airways due to inhalation of ozone causes a series of short-term, episodic, acute adverse health effects. These include shortness of breath, asthma exacerbation, and increased susceptibility to any number of respiratory illnesses due to the inflamed state of the lungs and airways. The images on this graphic illustrate this. On the left is a visual of air passages terminating at alveoli, with some explanatory notes beneath. On the right are photographs of a normal versus inflamed lung airway, the latter due to ozone exposure. Notice how restricted air passages are on the right image compared to the normal image on the left. Key summarizing points are provided here and on the next slide. The historical perspective leading to regulating ozone in the U.S. is from photochemical smog air quality problems that occurred mainly in the Los Angeles area in the 1950s and 1960s. Other parts of the country also had, and continue to have, ozone pollution events. However, Los Angeles, given its size and unfavorable geographic and meteorological setting, is especially susceptible. The image on the left is a photograph taken on a bad air pollution ozone day. The hazy, polluted air and women in the foreground rubbing their eyes depict the air quality on the day. On the right is a timeline of some key events surrounding the problem. The timeline shows the creation of various regulatory agencies in Los Angeles, California, and the U.S. motivated to control ozone and photochemical smog in the 50s, 60s, and 70s. Also, we note in 1955, a 1-hour concentration of ozone at 680 parts per billion was recorded in the LA area. This is the highest ever recorded, and is several times higher than the current 1-hour ambient air standard for ozone of 90 parts per billion. much work has been done to bring ozone levels to lower levels today compared to back then. However, as we will see, regulatory expediencies still exist. Quickly, we review the key ambient air standards for ozone set by EPA and California. There are both 1 hour and 8 hour standards. The 1 hour standard at 90 parts per billion and the 8 hour standards at 70 parts per billion. These standards are over short averaging times, 1 and 8 hours, which indicates that these are set to respond for short-term acute ozone inhalation health problems, which we summarized a couple of slides back. To conclude this overview, it is important to understand the typical vertical profile of ozone gas in the Earth's atmosphere. We studied earlier in Lecture 2 that ozone has a beneficial effect to life at the surface since ozone absorbs ultraviolet sunlight. This occurs in the stratosphere, roughly 20 to 50 kilometers above the surface, where ozone concentrations are highest. The stratospheric ozone layer is indicated on this graphic. Ozone in the stratosphere is often called good ozone, since it has a beneficial effect. Ground level ozone, on the other hand, is often called bad ozone because of the harmful effects of ozone if inhaled. We depict ground level ozone at the bottom of the graphic, called smog ozone in the body of the plot. Notice that the concentration levels, while elevated compared to levels in the troposphere, are much smaller than levels in the stratosphere. Ozone, whether created in the stratosphere, troposphere, or at ground level, is formed photochemically, that is, from chemical reactions with other gases involving sunlight. In the stratosphere, as we learned in Lecture 2, oxygen gas absorbs ultraviolet light, which breaks the molecule into free oxygen. This free oxygen then combines with molecular oxygen, O2, to form ozone. Ground level ozone, on the other hand, forms from a different set of photochemical reactions. These involve photochemical reactions involving nitrogen oxides, NOx, and VOCs, two air pollutants studied in earlier lectures. Both NOx and VOCs are emitted from pollution sources, whereas ozone is formed photochemically from chemical reactions involving these emitted gases. We therefore say ozone is a secondary pollutant, since it is not emitted directly, but rather forms from other pollutants that are emitted. The NOx and VOCs that form ozone are called ozone precursors. To summarize these basic concepts, this slide is presented. We distinguish between primary pollutants, which are emitted directly from a source, and secondary pollutants, which form in the atmosphere from chemical reactions involving primary pollutants and other compounds in the air. Ozone is a secondary pollutant. Its primary precursor gases are NOx and VOCs. For these reactions to occur, sunlight is required and high temperatures are favorable. Hence, hot summertime conditions are most associated with ozone air pollution events. Ground level ozone, formation mechanisms. Details of the photochemical reactions for ground level ozone will now be covered. We first start with those for ozone in the troposphere. As we have mentioned, natural background levels of air pollutant species exist that are non-zero in concentration. For ozone, natural background concentrations in the troposphere, below the stratosphere, are around 10 to 40 parts per billion. Note that this is much lower than values found in the stratosphere, comprising the ozone layer, and are lower than air pollution ground level ozone. The chemical reactions below for tropospheric ozone set the stage for understanding the higher values of ozone concentrations found at ground level in polluted urban areas. While we list these chemical reactions in a particular sequence, these in fact all occur simultaneously. First, nitrogen oxide that naturally exists in the troposphere reacts with atmospheric oxygen, O2, to form nitrogen dioxide. Again, the concentrations of NO2, nitrogen dioxide, would be small background levels, much smaller than in urban areas. The next two reactions we are familiar with. NO2 absorbs sunlight, particularly the violets and blue visible light, which dissociates the molecule back to NO and free oxygen. Recall the brown cloud of polluted air shown in earlier lectures, which was associated with nitrogen dioxide pollution. Next, the free oxygen combines with molecular oxygen to form ozone. This is the same reaction that forms ozone in the stratosphere, forming the ozone layer. The only difference is the manner in which the free oxygen is formed. Once formed, ozone then can react with NO to form NO2 and the O2 molecule. The third reaction creates ozone, while the fourth reaction destroys ozone. An equilibrium in which the creation and destruction rates roughly equal each other eventually is reached, which leads to roughly constant background ozone levels in the troposphere at around 10 to 40 parts per billion. Values are lower at night when sunlight is gone, and the second reaction that forms the free oxygen to create ozone in the third is not present. Summarizing points on this are provided here. The higher concentrations of ozone at ground level in urban areas result from two things: the addition of higher emissions of nitrogen oxides in urban areas, and secondly, the very important addition of volatile organic compounds, also emitted in urban areas, to the chemical reaction set. Recalling from Lecture 6, VOCs are vapors evaporated off liquid hydrocarbon compounds, gasoline, fuels, paints, and many other industrial chemicals. These are widespread in urban areas. Seen here is a list of the reactions for ground level ozone, similarly structured to those in the previous slide for tropospheric ozone. The first two reactions show how NO2 is formed. The first is the same as we saw in the previous slide. The only difference in urban air is that there is more NO in urban air emissions because of the increased emissions of NOx in urban areas that are typical. Hence, more NO2 is formed. The second reaction is new. This is a representation of a collection of many reactions between NO, nitrogen oxide, and various volatile organic compound species that are emitted in the urban air. Essentially, VOCs react with NO to form NO2. The end result is that compared with natural tropospheric conditions, much more NO2 is created in urban air through enhanced emissions of NO and the presence of VOCs in the urban air. The remaining reactions are as the last slide. NO2 absorbs sunlight and dissociates into free oxygen. Ozone is formed as free oxygen combines with molecular oxygen, and ozone is destroyed by reaction with NO. The end result is as before. An equilibrium is reached where ozone concentrations reach a certain level. However, in this case of urban air, a higher concentration than in natural background tropospheric air is achieved due to the additional emissions of NOx and VOCs and the resulting additional formation of increased NO2. Warm, sunny summertime conditions are favorable for these reactions to occur, in which cases ozone, O3 concentrations, can reach 100 parts per billion or higher. This graphic summarizes the points on ground-level ozone formation in urban areas, emphasizing what leads to conditions for bad ground-level ozone. First, sunlight and warm temperatures are required. Hence, summertime is what is typically referred to as ozone season by air quality professionals. Second, high precursor emissions of NOx and VOCs are required. Third, ozone concentrations are highest in unfavorable geographic and meteorological settings, with topographic trapping and inversion layers. We will see shortly how Los Angeles is one such setting. The end result, when all conditions come into sync, can be bad summertime photochemical smog episodes. Another pictorial summary is provided here. The types of emission sources responsible for precursor NOx and VOC emissions are indicated by turquoise arrows, while the magenta arrows are chemical reactions that occur when these emission species are incorporated into reactions. Combustion sources from both stationary and mobile sources are primarily responsible for NOx emissions. Hydrocarbon VOC emissions also come from mobile sources as unburned gas vapors, and as well from various other industrial and household sources where liquid hydrocarbons are utilized. The middle part of the graphic illustrates pictorially the photochemical reactions that take place involving sunlight and these emission species. The right side of the graphic illustrates the products of the photochemical reactions, enhanced ground-level ozone, and other photochemical smog constituents. Another important part of the ground-level ozone formation story is the diurnal cycle. That is the progression through a typical daytime cycle of these processes. This graphic sketches the buildup and drop of various species involved from sunrise to sunset along the horizontal axis. Emissions are high throughout the day, but often peak in morning hours associated with rush hour road traffic. The chemical reactions that form nitrogen dioxide from these emissions then proceed more strongly as concentrations of precursor gases from these emissions build up. As a result, there is often a time lag of a few hours between when NO2 peaks and when emission precursors peak. As sunlight and temperature become stronger during the day and NO2 concentrations grow, ozone formation then becomes more active, which again leads to a few hour time lag between when ozone is high and when NO2 is high. The end result is that ozone in urban areas is typically highest in mid-afternoon hours, around 2 to 3 p.m. Once the sunlight drops and the sun sets into the evening, ozone levels then drop as the sunlight that drives the photochemical reactions is eliminated. The following slides will illustrate these concepts further by looking at a case study of Los Angeles, an area where ozone episodes are common in summer months. Through this, we will see how the interplay of emissions, chemistry, meteorology, and geography lead to particular bad ozone problems and strong episodes in Southern California. This map illustrates the pattern of nitrogen oxide emissions, NOx, on a typical weekday in Los Angeles. The map is color-coded according to emissions in moles per day. Notice the emissions are spread out over the basin. From a careful view, however, of the pattern, one can see highest values along major roadways. Since NOx emissions are largely from motor vehicles, this makes sense. This map illustrates the pattern of VOC emissions on a typical weekday in Los Angeles. The map is color-coded according to emissions in moles per day. Notice the emissions are spread out over the entire basin, a bit more so than seen with NOx. In particular, less of a roadway signal is seen in VOC emissions compared to NOx. This is because there's a wider range of urban sources responsible for VOC emissions, being less centered on mobile sources. The graphic on this slide illustrates the typical daytime-summertime wind flow across the Los Angeles Basin. The upper left is a visual looking down horizontally, while the bottom right is a vertical cross-section looking from the side. A sea breeze blowing from the ocean inland typically develops over the LA Basin on summer days. This onshore sea breeze is driven by the combination of the Pacific high pressure system offshore and inland heating, as we discussed in Lecture 7. This sea breeze acts to blow emissions from the western and central Los Angeles Basin of NOx and VOCs inland over the basin, from west to east. High mountains, which prevent pollutant from penetrating further inland, also exist, which act to trap the pollutants from further eastward travel. The subsidence inversion also prevents vertical dispersion of pollutants. The end result is that pollutants become increasingly trapped both vertically and horizontally as they travel eastward across the basin. The resulting pattern of ground-level ozone concentration for 2 example days of poor ozone air quality in the Los Angeles Basin are shown on this graphic. The 2 days are September 17, 2000 on the left and September 22, 2002 on the right. Each map graphically depicts through color shading the highest or peak hourly ozone concentration that occurred during the day. Green shaded areas are areas where peak ozone concentrations on an hourly basis were less than 60 parts per billion. Reds are areas where the peak hourly ozone concentration during the day was greater than 125 parts per billion. And yellow and orange shading are where peak values are between 60 and 125 parts per billion. The key thing to notice are the areas of the LA Basin where ozone concentrations are highest. These occur in inland locations. This is because of eastward wind travel discussed on the previous slide, combined with the time lag between when peak precursor NOx and VOC emissions occur, which are in mid to late morning, and when sunlight and photochemical reactions are strongest that form ozone from these emissions, which culminate in peak ozone concentrations in mid-afternoon. Since the emitted species and chemical reactions that act on the air are flowing inland with the sea breeze, by the time the ozone forms in the mid-afternoon at its highest value, the polluted air has traveled from in the wind eastward across the basin to inland locations. Ozone and other photochemically produced air pollutants are therefore at highest concentrations at the shown inland locations, Riverside, San Bernardino, and other areas inland in the Los Angeles Basin. The topographic bounding from surrounding mountains to the north and east then trap the polluted air from further eastward transport, hence leading to buildup in the eastern LA Basin. An important thing to note from this is that the area where emissions are strongest, in this case with ozone within the western and central LA Basin in the city center, and where concentrations are highest, which occur inland in the eastern LA Basin, are not the same. This is typical of ozone air pollution generally, and indicates that the location where emissions need to be controlled to reduce concentrations is often not the same as where concentration impacts are highest, requiring the need for control. This causes interesting regulatory problems, since the jurisdictions where emissions are controlled is not always the same as where air concentrations need to be controlled. The point from the previous slide related to inland travel of air pollutants associated with ozone in the LA Basin is made more explicit by revisiting the slide previously shown in the lecture on the diurnal cycle of precursors and ozone. Recall the time lag discussed previously, where NOx and VOC emissions, precursor emissions, peak in morning hours and ozone in late afternoon. These time lags are due to the combined effects of when emissions tend to be highest and when sunlight and temperatures are highest in early afternoon that drive the photochemical reactions that form ozone. Mapping this in space in the LA Basin, NO and VOCs are highest in morning in the western and central LA Basin, and due to the sea breeze and the time lag discussed, the peak ozone later forms in the afternoon in inland locations in the eastern basin, as the polluted mass travels with time inland with the sea breeze. Ground level ozone, regulatory efforts, and emission controls. Ozone is among the criteria air pollutants in which ambient air standards have to be met. As we have mentioned in previous course material, ozone is among the criteria pollutants that air districts across the country continue to be in non-attainment with. The situation in year 2015 across the LA Basin in terms of compliance with the 8-hour ozone standard of 70 parts per billion is shown on this graphic. Shown on the map are shadings of the number of days during 2015 when the 8-hour standard was exceeded. The black dots on the map are monitoring stations across the LA Basin where compliance with these ambient air quality standards are checked. Notice how the map of exceedances closely aligns with where the ozone concentrations are typically highest across the basin. Specifically, from 40 to 60 days per year, there are 8-hour exceedances of the ozone standard. These occur in the eastern LA Basin, around the areas of San Bernardino and Riverside. These days almost always occur during summer, which consists of around 90 days for 3 months times 30 days. This implies that 40 to 60 exceedances out of 90 days per summer therefore implies almost every day or every other day there is an ozone exceedance in the eastern LA Basin during summertime. Further west, we see less exceedances, between 0 and 20. This is because the sea breeze pushes the polluted air emitted eastward. So although there are more emissions in the western and central basin, there are less exceedances of concentration standards. As a result of the exceedances shown on the previous slide, the South Coast Air District, which covers LA Basin, is a non-exceedance area with respect to the 8-hour ozone standard. Air districts that exceed standards must then develop, together with state and other agencies, a very comprehensive plan called a State Implementation Plan, where a plan by which air pollution emissions will be reduced to lower concentrations below ambient air standards is developed and communicated to the public. The web link for the South Coast Air Quality Management District State Implementation Plan for 1 and 8-hour ozone standards is shown here.